Okay, so today we'll look at some power reduction techniques. We have already been looking at some of them, but today and the next lecture we'll look at some additional techniques. But before we do that, let's review the basic equation which governs the power dissipation in a CMOS chip. And power dissipation basically has two components: the dynamic power component and the static power component. Dynamic power component is a component which is associated with actual activity, dynamism in the circuit. Static power component is a component basically of power which is consumed no matter what happens in the chip. As soon as you connect the chip to a power supply, you start seeing a reading in your ammeter, and it's essentially consuming power. Now the equation for dynamic power is this. Essentially it is summation of alpha I Ci V square F. Basically I is the circuit node. Every gate in the chip, if you take the output of that gate, that node, we can label that node as I. So the gate connected to that node we can call the gate I, and that node has some capacitance Ci, self capacitance of the gate which is driving it, and wire capacitance, and all the loading of the gates to which this wire is connected to. The loading means the input capacitance of those gates, right? So that is Ci. VDD square is the VDD is the power supply voltage, F is the frequency at which the chip is operating and the nodes are switching, and alpha I is the probability of the node switching from 0 to 1, the activity factor. So this is the dynamic power, and the static power is that node I is being driven by a gate. That gate, the ith gate, has some continuous power current consumption from VDD to ground. It is just going through the through that gate. Even though that gate is a CMOS gate, and one of the stacks of there's a pull up and pull down. One or the other is supposed to be off, but the off one always will have some leakage, and that leakage consists of leakage, subthreshold leakage to the gate, where from the drain to the gate you'll have, and then the junction leakage. So these are kind of the main leakage components. And as we had discussed, the leakage in that gate I depends on the input vectors to that gate. As we saw in the last class, for any gate, based on the input vector, the leakage currents can be quite different. So it really depends on that. The threshold voltages. The reason I put a bar on top of these is that just to say that they are vectors. Okay, nominally we'd have same threshold for all the NMOSs and same threshold for all the PMOSs, but the NMOS and PMOS threshold could be different. Okay, so it's a two-dimensional, two-tuple. But in addition, you could potentially have different threshold voltages for different transistors in the gate. It's not common, but it can be done. So that is why you have a vector of threshold voltages, and then of course the supply voltage. Supply voltage also determines the leakage current, not just the power. Power of course is I times V, so power is clearly dependent on voltage, but also the current itself. You know that, if you recall, there is a Dibble effect. The VDS, the off stack which is there in the CMOS sees a complete VDD voltage across it. So that will lead to modulation of the threshold voltage of the transistors, and hence the leakage current, because the subthreshold leakage is exponentially related to the threshold voltage. So this you again sum over all the gates. So as we said, N can be, depending, some of these typical chips will be in the millions, so very large numbers. So this kind of analysis has to be basically done through automated tools. So that is where in digital design you basically have to have whatever techniques you come in for analysis has to be incorporated in the design tools. Now basically these equations essentially kind of tell you, if you want to reduce power, you have to see each of these terms and reduce it. Okay, so let's start with activity. We already reviewed how you can reduce the activity of the clock signal, because the clock signal every period has an up transition and a down transition. So it has an activity of 1. For certain, that the clock will have a transition. So what you do, as we saw in the last class, you shut the clock. If you know that that particular piece of logic is not required, that whole group, you can turn off the clock. and you turn off the clock by just putting an AND gate, and you have a gated clock coming out. But make sure that the signal for the AND gate is kind of controlled, and the transitions on that signal happen at the right time. Okay, so that you don't have false edges or edges in the clock, gated clock signal at the wrong time. So that is clock gating. Not only does it reduce the activity in the clock signal, but all the flip-flops to which this clock is connected to, their outputs will also be frozen now, because they will only change when clock is there, and then those flip-flops will feed to all the combinational gates. None of them will be. The whole block will be no activity. Okay, so that is a simple technique which is basically widely used. So by you kind of, now it's a given, you cannot do clock gating. In addition, for a non-clock type signal, under certain special, there could be special specific places where you can look at how to maybe change some coding, essentially recode the information. For example, or reorder things and so on. So like, let us say that there is a node I which is seeing this transition 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So, every other cycle it goes to 1. So if you see that there are 5 transitions here, 0 to 1 transition, right? So the activity is half. In 10 cycles, 5 of them have 0 to 1 transitions. So activity is alpha I is 0.5. Suppose you could reorder that, right? And you put all the zeros in the beginning, all the ones in the end. Then you just have 1 transition. Activity has come down to 1/10. Now, when is this possible? It's clearly not possible all the time. It's a very specific thing. If you have some random node you pick in a circuit, you cannot really adjust things like this. But for example, say you have a bus and you want to send information over the bus. What is a bus? Bus is a bundle of wires. Maybe it's a 16-bit, 128-bit, 256 bits. In a chip you can have very wide buses, 512-bit, 1024-bit. You can have very large wide buses, and you're sending information across the bus. Maybe you're sending it from, maybe you have an array of cores, one core to another core, and you can look to see if you have a packet of information to send. Maybe you can change the ordering, but then you need to know at the other end how to recover that. Maybe there is another way to encode the information where the ordering is not changed, but it is encoded, and the other side you decode it. For example, in the case of one popular place where this is put is instruction reordering. You have a memory from which you fetch instructions, and the instruction, maybe 32-bit instruction, comes out from the memory, goes on the instruction bus, comes to the processor. So there is a sequence of instructions, but maybe you look at the sequence and you say, okay, instead of I1, I2, maybe I do I2, I1. Provided your processor and your program is able to deal with that. Sometimes the instructions don't have dependencies, and they could have or happen in any order. So then why not use the order which will minimize the transitions? So these are all very specific, kind of the general idea. But if you want to apply it, you have to really look at the specific case to see how to apply. Coding of counters. You have a counter. Maybe it's kind of going in a certain way, but maybe what you want is a way by which you index through a sequence of states, and that indexing need not happen in the binary fashion which maybe there is some other way, or like maybe you do something called gray coding where so these are some of the things which you could kind of look at to reduce the activity factor, but these are very specific to application. These are 5 0 to 1 transitions. 1 to 0, see, alpha I definition is 0 to 1. Okay. So here is another technique, what I call variable hardware. What I mean is, you design your chip, you design your circuit, but the amount of hardware you use for your computation, you kind of change based on what is required. Okay. Now, really, is it reducing alpha I or it is reducing alpha I times C? It doesn't matter. Essentially, that you are reducing the amount of switching capacitance. So, for example, you could have you have a 8-bit bus or a 16-bit bus. Maybe it is an application like a filter, right? You're doing a filter. And you decide that, look, I don't need a 16-bit word length. Maybe I can use a 8-bit word length for certain kinds of things. So you can then suppress, or you can put zeros in the other 8 bits. So now what you have is basically you have no activity in those 8 bits. So you have reduced the activity factor. Again, it's very specific, application specific example. You could have segmented architectures. Again, you take it to the next level where you say that, look, I know that I need a 16-bit data path, but I'm going to make it out of 4 groups of 4-bit data paths. And then you can shut off the whole things. I mean, if I want to do only 4-bit operation, you shut off the others, the remaining higher 12 bits and so on. So that kind of thing could be done. As an example, here is the example of a filter whose tap filter length is adjusted. Okay, maybe depending on the actual condition, he wants to, instead of using a very large tap length and very sharp cutoff, maybe he finds that I can have a slow roll off for that filter. So then he wants to use less number of taps. So basically, so what is being done here is that, what is a filter? A filter, you might have all studied in your undergrad, is multiplying sigma ai xi, right? That's what you do. So you have, what you have here is, right, you have the coefficients coming in out here. So it's a 15, it's a 30 tap filter, and so what he does is that, if he wants to if he wants to reduce the tap length, he can, for the higher tap lengths, he can set it up so that zeros come out. Okay, so that way the tap length can be adjusted. So when you pass zeros, essentially you're not having any activity. You can say, you can also do clock gating. That is not being done, but you can kind of, what this is doing is, he's basically passing zeros. He's switching, he's instead of passing the data, he always sets the mux to always give a 0. So there is no activity in these taps. So suppose I want only up till this tap, everyone else after this you pass a 0. So there is no activity in that, no activity in these buses, no activity in these multipliers, adders, multipliers, etc. So you have really suppressed the activity in a portion of the chip just by setting the values to be fixed values. And what happens is, because these are all zeros and the nature of the computation is kind of addition, because you have each, in a filter you add products, and if you add a 0, nothing changes. So it just comes out to be a very simple way of doing something like this. You can also have coefficient 0, but then what that does is, only from the multiplier onwards you will have no activity. So yeah, you can also do it that way. Yes. Here is something which we will discuss later. There is a carry save adder tree. This is kind of used when you want to add a number of numbers together. Typically when you add 2 numbers, you use, the simplest way of adding is what is called a ripple carry. Like how would you do by hand? You start from the least significant digit, you add, carry, you put, and so on. So the carry keeps rippling. In a carry save adder, you don't explicitly add the carry till very end, and it's very useful when you have a number of numbers you want to add together. So you do it in the carry save fashion. We'll kind of look at it later in the course. So we'll not worry about the other things out here. I mean, essentially, the main, I just wanted to point out one particular approach by which this variable hardware is implemented. Here is another way. Suppose I have this data path and say into this filter, and I want to adjust. I know that maybe into this filter or this, especially these kinds of things are useful for signal processing blocks. Okay, where you know that you anyway have noise to deal with. So when you change the number of bits, what you are changing is what is called quantization noise. You change the amount of quantization noise you are using. And if you find that you can tolerate more quantization noise, you reduce the bit length. And this is a simple way of reducing the bit length, where what is being done is the input to the whole logic is right shifted. So then everything in the top basically has static values, and there is no switching activity. Static values. So what I'm saying is, say this was the original word, and imagine that there is some kind of a computation block below this. But instead of sending this word like this, you decide to truncate some number of bits because you think that that is not essential for that portion of the computation. So you right shift it and then you send it. Exactly, you pass it. So the same logic, you will not change anything in your logic, but what you have done is the data which you are feeding in, you are truncating so that the higher order bits of the data are not toggling, they are remaining static. So you have reduced the activity factor that way. Question is, yes, the sign bit is replicated. Yes. So it's very specific because here he is using 2's complement. But the idea is essentially, suppose you had a signed magnitude representation, then you would basically, instead of replicating the sign, you would just have zeros or something like that. These are all what I would say is no, basically the question was the sign is being the sign itself, the variable bit width. Okay, so in the signal processing systems, okay, the data, you're processing the data, you're applying some algorithms and transformations on the data. Now you know that that data is a digital representation of some physical signal. Okay, a physical signal is analog, and whenever you capture it in the digital world, you are going to use some number of bits. As soon as you use a finite number of bits, you have essentially what is called quantization noise. A true analog value is going to approximate with a digital value. Now, the more number of bits you use, better is the approximation. Now, what is the right number of bits to use? It really depends on the overall application context, because the difference between the digital value and the analog value, that error is called the quantization error. And your overall application might be able to tolerate some amount of quantization error. Now, if the quantization error you can tolerate is different in the runtime, you are actually using the system, maybe it's a DSP, for some application I just need 4 bits, some other application I need 8 bits, some I need 16 bits. The same, but different applications need different because they are just dealing with different signals and they are doing some different things. Now, when you design this kind of a chip, you design for the highest resolution, right? You'll say, okay, I know 16 bits I need. But when I don't need all the 16 bits. If I still use 16 bits, I'm just wasting power. So that is where that is the overall theme or concept of variable or adaptive hardware. When you design hardware or when you design anything, you can have designed for the worst case. But if you provide a way of adapting where the actual system can adapt to the actual requirements, then you will be more power efficient and energy efficient. So this is one example where the adaptation is happening of the resolution, and this is one way of doing it, is just by right shifting. So that's basically. So just taking a step up, if you want to be energy efficient, right, there is an optimum speed at which you should work, an optimum way in which you should utilize resources. You should not be too fast, you should not be too slow. Okay, we'll kind of see that in the next lecture. It has to be just in time. Okay, what I call be just good enough. So, but to do that, you have to have the ability to adjust yourself, right? For this course, maybe you put in a little extra effort. Maybe some other course, you say, okay, I don't need to put that much work, right? Just before the day of the exam, I'll study. You guys already know how to do that. So why not apply that when you design systems, right? Where the system is designed to be efficient across a range of demands of what is required. Yeah.
The explicitly address multipliers are constant number of gates, samples, and partial fractions. We define it according to the ITP rules. How can we change these values according to the requirement?
What I'm talking about has nothing to do with IEEE standards and so on. Okay, all we are saying here is, you basically, for example, here you might still use a IEEE compliant multiplier. Maybe it is a floating point unit, and you have IEEE standards floating point operation and unit you're doing. But what if the dynamic range of the signals, you know that I don't need that large a dynamic range? Then all we are saying is you don't change anything in the unit, you just give a reduced range. And how do you do the reduced range? And make sure the other bits you just put to a static value, possibly 0. So that's all. Nothing is being said about the standards compliance or non-compliance or anything. It's just a way by which you can reduce this effective switching activity. Alpha I Ci product, in some sense we are reducing. Or alpha I we are reducing to 0 for some of the i's, right, essentially. So I also mentioned that you could do what are called microarchitectural changes. Okay, I want to just give you one particular example because otherwise it will be too vague. What do you mean by that? Or rethink the algorithm, how you implement the algorithm. So here what I want to do is, there is this, I kind of take the example from a filter. You want to implement a filter. What is a filter? A filter is basically x1, x2, xk as there. It's a sigma of ak, xk. So x is kind of coming in, time samples, and then you're generating the y, which is a, you multiply every sample with a coefficient, then you sum it over some number of samples. So this is a standard digital filter, right? So we already saw in that previous example of how to implement this filter, right? One way of implementing this filter, which is you have these coefficients. So these are the samples coming in, and then these are the coefficients coming in. This particular filter is a slightly special filter, but let's not worry about it because there are both this and this are added, and then there is a coefficient multiplied. It's a 30 tap filter, but only 15 coefficients are there. It just turns out that this particular filter is very specific, where the coefficients are symmetric. C0 and C30 are the same, and so on. But it's a very special case. But the point is that this is what I would say conventional way of implementing the filter. You have a number of multipliers. In fact, for k tap you have k multipliers, and you have coefficient coming in as one input to the multiplier, the data coming in for the other input. So just ignore this plus out here, coefficient and the data coming in, and then you add it up, right? You have to have a big adder. You would implement it as a carry save adder, or you can have, you add two at a time and then combine it and so on. So this is what a filter is. So that's what a conventional approach is, right? So for example, this is probably you guys know how a filter works. Now, is there a different way of implementing this filter? And the answer is yes. There is this notion of distributed arithmetic. Okay, so it's kind of interesting, so that's why I kind of want to just go through it, how you can kind of rethink, you look at the algorithm and rethink how you want to implement it, and when you do that you get a totally different hardware realization of the algorithm. So let's again look at the equation for the filter, right? Y is equal to sigma k equal to 1 to k, ak, xk. Now xk's are binary, in fact all of them are binary numbers, and any binary number, if it's an n bit number, essentially you have bk0 till bkn minus 1. It's a vector. There are n bits in the vector, and of course he is taking bk0 as the sign bit. Now some of these manipulations are not very important for the purpose of our class, because I am more interested in the concept rather than the detailed signal processing stuff. But basically let's just kind of go down a little bit more. Xk any binary number essentially has this value. Any 2's complement binary number has this value. That is the most significant bit. There's a minus sign plus sigma n equal to 1 to n minus 1 bkn 2 to the minus n. Okay, so this is the value of a binary bit pattern which is supposed to be a 2's complement, which is interpreted as a 2's complement number. Okay, now you take this representation of xk and you put it into this equation. Okay, all we are doing is we are taking this xk, which is written like this, and we are substituting it into the equation for the filter. So now you have y is equal to sigma k equal to 1 to k, ak times xk, which is written like this. You spread it out, you take ak and multiply it in, and then ak gets multiplied with each bit. Remember, each bkn is a bit. Okay, it gets multiplied by bit. So now this will be easier to see in a, to visualize this in a slightly graphical form. But the idea here is that what is being done, we'll look at this. So this is the so if you take any particular, let's ignore the sign for now. If you take any particular xk, each of this is x, each horizontal row corresponds to a xk. So it's a1 x1, a2 x2 till ak xk, right? That is what the equation was. So that has just been written in this form. We have just expanded it in a bitwise expansion. The first one is b11, b12, b1n minus 1, and a1 is multiplied with each bit. Okay, the second one is like this, and a2 is multiplied with each bit, and so on. And if you see, everything is added together. But instead of adding it this way, you add it now column wise. When you add it column wise, what do you get? You get that here, for example, 2 to the minus 1 is common because that is the position of the least significant bit. So first you add all across the least significant bit, then the next one, then the next one, and so on. Sorry, least significant is 2 to the minus n minus 1. So you add column wise. And when you do that, this whole thing is collected like this: b11, a1, b21, a2, etc., etc. The same sum, but it is now being represented in a transformed way, right? So the answers for these two will be exactly the same, but the way you do the calculation is a little different. Now you'll ask, okay, so what? What is being achieved out here? Now, one thing is that it turns out now that what are you doing out here? What you're doing out here is, see, a1, a2 till ak are coefficients for the filter. You know what those coefficients are. And b1, this product, the sum of this product, each b1 is either 0 bit or either 1. So you see out here, you have the way you can combine a1 till ak. There are 2 to the k possibilities in which you can combine a1 plus a2 plus a3, or a1 you skip a2, or because each position is 0 or 1. There are 2 possibilities for each position, and there are k such positions. So you have 2 to the k possible combinations of the coefficients a1 till ak. So the idea is, why not calculate them upfront? Let's calculate and keep it. Then you use the bit, this bit b11, etc., as a index into a memory. Okay, so that is basically the idea of the distributed arithmetic. So what you have is, say in this example, you have 4 bits. There are 4 coefficients, and these coefficients are set up. You have all 16 possibilities. All coefficients are added. a1, a2, a3, a1, a2, a4, etc. You can go through and you will see all combinations are there, and it's all preloaded in the memory. Then you use the bit pattern to just index and get it. So you have n cycles because there are n bits for an n bit number. For each significant bit significance position, you have this. You look at all the bits, you index, you get it, and so on. So what you have done is you have removed or replaced multipliers with table lookup. Now, is it useful? Is there any benefit, etc., etc.? You can ask the question. But the first point is that to note that the same answer you can get by rethinking how you implement the algorithm in a completely different way, right? What was done through multiplier adder is now just lookup adder. And so the point is there could be different ways of realizing and getting the same answer. And now you have to look at the choices, what is the plus, what is the minus, etc. Of course, it turns out that if you see the growth of the size of the table, it's exponential. So there is that issue. But it is very low activity factor, because whenever you have a memory, none of the bits, nothing except for one row, everyone else is just quiet. So the activity factor is very good for memory. But it can have a lot of leakage, and so there are pluses and minuses and so on. So this kind of thing is used. People find it very suitable for FPGAs, which have a lot of memories anyway lying around. For chips also, some people have tried, and up to a certain sized filter, they find it to be more energy efficient to take this approach versus the standard approach. Pardon? See, this will be basically not necessarily. See, again, it depends on the size you have and so on of the memory. Right. So for smaller sizes, again, this will have benefit over the multiplier. But larger sizes, the exponential growth of the SRAM will basically, you'll give it multiplier. Right. You just load the RAM. You reload the RAM with you have to do all the combinations, calculate and upload it. Then you'll have it.
Even having a lookup table, you have to keep, there will be capacity charge leaking. Again, you have to charge them.
Correct. So you will have memory elements, and depending on how the memory cell is designed and so on, if it is a leaky cell, then again you have a lot of leakage. But no. See, there is when we discuss memories, we will discuss about refreshing and so on. Not boosting, refreshing. You can lose memory, but for static, what is called static random access memories, you don't have to do refresh. It's always information always stored. But it might leak. When I say leak, it doesn't mean the information gets leaked out. There is current leakage and you have power.
What about the voltage that will be stored across the capacitor? Because now these capacitors are not leaking.
No. So yeah, we'll discuss that when we get to the static memory. You are absolutely right that at the end of the day, even information which has to be stored as charge on the capacitor. But the structure of the circuit is such that there is always leakage. You cannot avoid leakage, but that leakage is compensated in a way where the information is stored. I mean, the voltage across the capacitor doesn't degrade. It is held static, but there will be some leakage. Okay, for example, you take an inverter and you put the 0 at the input of the inverter. You look at the output of the inverter. Output of the inverter will be 1. There is leakage, but it will be held 1 because input you have kept as 0. So that's how, even though there is leakage, the output is held to be 1. So that kind of here it should be stored. So imagine you have two inverters, one connecting to the other, two back-to-back inverters, right? So one of them, if you put input as 0, the output of the first one will be 1, which will again be 0. So it is a self, each will help each other. Each will help the other. So that's basically the structure of a memory cell, which is also what you have seen in the case of a latch and a flop, right? Two back-to-back inverters. Of course, in the case of a flop, you have a gated inverter, but that's basically what it is. So it's just to kind of, give a concrete example of how you might also have the opportunity to rethink how to implement the algorithm, or rethink the algorithm which implements the function, right? If you want to. So, static power reduction. So we kind of look at this concept of, there are a number of techniques again for static power reduction. input vectors during standby state, stacking, multiple threshold, transistors, channel length, power gating, etc. etc. So we kind of briefly looked at some of these in the last class. Let's look again in a little bit more detail. And we saw how in the case of a NAND gate, right, which has two series NMOSes in the pull down stack, the lowest leakage happens when both the NMOSes are off. There are two series of devices. So there is the effect of stacking, because what happens is that both of these are off. So if there is some small leakage current going through, there will be some voltage drop across N1. Right? So Vx, the intermediate node, will rise up. When Vx rises up, it will cause a negative voltage for N2, negative gate source voltage. That will reduce the leakage even more. So there is a kind of, this stacking has this beneficial effect of reducing leakage because of this. So you can have leakage reduced by a factor of 10 or more because of stacking. Now you have natural stacking in an AND gate. But suppose you didn't have an AND gate, suppose you had an inverter or some other gate, what do you do? So what you do is you create stacking. So imagine that you had just one NMOS connected to ground of a certain width. You take that NMOS, you break it up into two series transistors, each of width W by 2, and you say you short both the gates. So from a functional point of view, it's the same. You had an inverter, input was connected just to a single NMOS transistor. Now you have this other inverter structure where you have, instead of a single NMOS, you have two NMOSes in series whose gates are shorted together. So the input is still going to both of them. So when the input goes high, both of them turn on, output goes to low. When input goes low, both are off, output remains high. So functionally it's the same. But because you have done stacking, the leakage is reduced. But what is and also what you have done is the width, it was W in the previous case, here you make sure that total width is still W. So the capacitance seen by the previous guy still remains the same. So the gate who is driving this, for that gate, doesn't know what has happened, but this gate, what has happened is you have broken it up into two and you have done this. Of course, the problem is your speed will go down for this gate. So as I said, it's always a trade-off. Power, when someone says I've reduced power, immediately you should think, okay, what is the cost? Something has happened, delay has gone up. Most of the techniques will always trade off power reduction versus speed reduction, right, or delay increase. Because now in this path, delay will go increase because the pull down resistance is larger, etc., etc. Okay. So, but then you might have paths which are not critical where you can apply this technique. That's what I'm saying. It will reduce the current, and so this gate will become slower. So that is the price you pay. But then maybe you do it where it's in a path which is not a critical path, so you can afford to take the hit and delay. The overall system delay doesn't change, or system delay does change, but it's a trade-off you're willing to make because the gains. Remember when we said in sizing, when you do minimum delay sizing, you can end up with an energy which is pretty large. And if you back off from the minimum delay sizing, you can get a substantial reduction. A small back off, a small increase in delay can reduce energy quite a bit. So that kind of trade-off, you might want to do. Of course, you can also say, why not increase the channel length? I'll make the channel length 2x. Okay, so that you can do also, but sometimes what happens is that if you recall the threshold voltage as a function of channel, you have short channel effect and reverse short channel effect. Sometimes threshold goes up, sometimes threshold comes down depending on the process and so on. So if you want a truly portable design, this might be better, where all channel transistors are minimum length, but then you do it this way, you take the design, put it in another process, you can still expect a two series transistor to be slower than a single transistor. Whereas a transistor with twice the length, because of the reverse short channel and short channel effect, depending on the process, you might not get what you want. Right? So that is also something to keep in mind about portability of techniques. Are they portable across process generations, process nodes, you do it, manufacture it with IBM, then you want to move it and manufacture it with Taiwan Semiconductor and so on, the same design, right? So you want to try to keep things portable so that you can quickly port. So the idea of so when I know that some gate is some piece of logic is going to standby state, right? Because you did clock gating, that whole block, the floating point unit, it decided to shut off the clock because I'm not using it. When you shut off the clock to the flip flops, the whole combinational logic, there is no activity because clock is not there. There is no activity because all the data elements are fixed to some value. But what value should they be fixed to? Because say here I had AND gates out here. We know that the input of the AND gates, giving them 0, 0 is better than giving them some other bit pattern, right? So if you can intelligently figure out the correct bit pattern to put and feed it to your combinational logic, you can actually reduce the leakage in that standby state. So that is basically the idea of standby state vector application. So you have to analyze your combinational logic, because this combinational logic will have a lot of gates deep inside all the way down. Now a gate which is closer to the inputs, that inputs you can easily control because they are coming directly from the flop. But some gates which are deep inside, even though you would like to have a specific, that gate, this bit pattern at the inputs will give me the lowest leakage, it might be hard to get to that bit pattern because there are a lot of constraints, right? You try to get that, but some other gate will get some other bit pattern which will be higher and so on. So there is this problem. I mean, from all the possible feasible, if you see, if I have n flip-flops here, you have 2 to the n possible combinations. Which of them is the best, right? So typically in this all digital design, you have all, this is the kind of situation, you have all very computationally very hard, complexity wise very hard, but people have come up with clever heuristics. So when you do, people, if you are interested in research in algorithms, computer aided design algorithms, these are the kinds of things you will explore. How do you quickly find out the right input vector which gives you most of the benefits you want? Sometimes it may not be optimal, but as long as it's kind of reasonably good compared to just doing something, simple, this might be, it will be worthwhile. So that is called heuristics. You apply heuristics to get. So now once you figure out through some analysis, okay, this is not, when you do the design, you know what the logic is, you can do analysis, and because each gate, there are certain bit patterns which give you the best, and you put all of this together and you come up with saying this is the bit pattern which will give me the best reduction in the standby power. That bit pattern you need to apply. How do you apply? You apply it here. So you have to modify your circuit now. You have to put a mux here. So these muxes are there. And now it turns out that one mux is always there. Okay, that is for what is called scan testing. Okay, scan testing is something where it is what is done is you serially chain these flops. So when you want to test this combinational logic block, when you manufacture the chip and the chip comes back, you want to check if everything is okay or not okay. See, you're thinking, you're basically making like chips which have multi-million gates. Every gate has to work pretty much, otherwise chip is dead. Because as a designer, you never think of, okay, what if that AND gate doesn't work? You never think like that. You just say, I'm going to add, multiply, etc., etc. You assume that everything is going to work perfectly, right? And remarkably, that is what is happening. The manufacturing industry is guaranteeing that sufficiently large number of chips work perfectly, and you can, it's still economical to do it. So, but to check that, people do what is called scan testing. So when the chip comes back from fabrication, you can put in specific bit patterns out here, and you can test. Once you put in a particular bit pattern, you get a particular output bit pattern that you again capture and serially scan out. Then you check, is this what I'm supposed to get? Like that, there are a number of test vectors, what are called, which you put in. You see what outputs come, then you check. That way, then you are happy that if everything matches, the chip is okay. Now to put in those test vectors, because these flip-flops are all deep inside the chip, you have million, half a million flip-flops. You cannot have so many. I mean, how do you put in information and set a particular pattern? You do it in a serial way. All flip-flops are chained essentially. So one by one you shift it. So it's a slow process, but you do it only during testing. Shift it in, let it settle, check the output, shift it out. I mean, shift it out, check the output. Like that you keep doing. Now what is being done is that is modified a little bit. You put one more flop mux here, and the standby state vector is introduced out here. When you do that, when you go into the sleep mode, what you do is you put in the test bit here, and you have to. So if you want to apply the standby state vector, looks like here I need to go into sleep and do test. This is what this person is doing. So, and then that vector comes. Okay, so that's how, what you do is before you turn on the clock gating, one cycle before, you set this up. And this MLV1 till MLVM plus K, these are statically determined during design time. So this could be hard coded 0101, because once you have a particular combination logic, there is a particular input vector which will give you the minimum, so you just hard code it. Before I enter the standby state, before I shut off the clock, one cycle before I apply this, so that this value gets flopped in and presented here. Then I shut off the clock. Question? For the standby state, you do parallel. The serial one is only during manufacturing test. Scan in. During manufacturing test, the chip comes back, you put it in a tester. The tester basically does all this. It will scan in, scan out, scan in, scan out. There will be thousands of vectors it will scan in, scan out. Pardon? No. So the question being asked is, can it check only sequential logic? So here I don't want to get into discussion of testing and checking, but because this example uses that, I just wanted to explain that. But the scan test is done to test all logic, sequential combination. It's really, nothing to do with sequential combination. It's just testing all gates, or as many gates as possible. You can never be 100%. You want to, what is called coverage, get very high coverage. What if you wanted to store the state? Because when I put in the standby state, whatever was there before is lost, right? So then you can do something simple where whatever was there, you store it. You have to have another set of flops to store that state. Okay, so before you do, so whatever is there is mirrored out here in one cycle later. Yeah. And then you put in the standby state. And then when you come out of standby state, you first take this and put it in. Then you let the things go. So that is the. So if you see out here, the standby state is, vector is also scanned in. It's not hard coded, it's scanned in. Then it is stored out here. And then it's like a ping pong. You put it in here when you enter standby state. When you come out of standby state, you put it back here. No, it's just you go into standby state in a single cycle, but the information which is stored here after manufacturing test, what you do is you are happy the chip is work, you want to give it. No, actually what you have to do is, then in this kind of a thing, when the chip is powered up, somehow the standby state vector has to be entered here through the serial interface. Maybe there is a ROM, BIOS ROM, or some ROM. So at the beginning it goes, reads, and this kind of, all the setup is done. And then as the chip is running, it goes into standby state. From here it goes here. When it comes out of standby state, from here it's put back here. So it's ready for the next standby state. Pardon? Yeah, per ASIC it's fixed. That's right, absolutely. So maybe, in fact, yeah, so the problem here is that, actually what I said is also not correct, because the way he's doing it out here, this state is always getting refreshed from this. One cycle later. So the standby state vector, the knowledge of what is the standby state vector has to come in through the scan chain all the time, which is not good because it will take a long time to get into standby state. So there, if you see, so this figure by itself has to be modified actually for a complete implementation. So maybe this has to be a 3 input mux like before. Maybe you have a 3 input mux where the standby state vector is hard coded and that comes. So because if you try to scan in the standby state vector, it will just take a long time. If I know that I'm going to go into standby state, then why deal with all this input vector? Why not just disconnect the power supply to that portion? That is the easiest, right? That is the best. Use turn off the switch. So that is the idea of this power gating. Very simple idea. You have these switches which connect the internal power to the external power. So you just turn off these switches. Okay. Now these switches, these are called power gates. Again, this has now become a very popular technique. A lot of chips use this. Idea is very simple, but actually the implementation, we are not going to too much detail, can become quite complicated. Okay. And the reason is essentially to do with sizing of these switches. How big should you size those switches? Because those switches are in the series path to the power supply, right? Whenever this block switches gate, it draws current from the supply. That current has to come through these switches. So they put series resistance, they'll degrade the performance. So how much too big? If you put too big, too wide, too many of these, area will go up. You will have low resistance, which is good, but area will go up. And area is equal to money. Okay, basically, it's not, you can't just make the area go. But then, if you put too less a size, then this might not run at the speed you want and your customer will not buy the chip. Pardon? Now the question is, what about these transistors themselves? Will they not have power loss? Of course, yes, because even though these are off, they are still in the path and VDD is there. So there are a couple of things. One is, these transistors usually have higher threshold voltage, so the leakage is low. This logic will be low threshold, but these transistors could be higher threshold. Even if they are not higher threshold, because of the series stacking effect, the leakage will be less. Or maybe sleep voltage is, instead of VDD, it could be slightly above VDD. For PMOS, for NMOS, when the gate voltage is less than 0, it will turn off the device even more. Similarly, for PMOS, if the gate voltage is above VDD, it will turn off the PMOS even more. So you could do things like that, higher threshold, higher, etc., etc. And one thing you have to watch, so there is that, it's a tricky problem because the current consumption of this gated block, because you have to size this such that the IR drop across this is kept small. But what is the I to use to calculate the IR drop? I is a time varying. If you remember the current drawn by an inverter when it switches, the current is consumed only during the switching. It's like a triangle, right? So the total current will be sum of all these little triangles. Now if every gate switches, then you will have lot of triangles adding up and you will have the instantaneous current can be very large. But not all gates switch. Activity factor, as we said, is small. So that becomes a tricky thing. If you make the assumption that everyone switches at the same time, you will end up with the current which is so large that putting a power gate of that size will be not feasible. I is so large that I times R means R has to be very small, size has to be very big. So that estimation of I is a tricky thing because I can have two gates switching in the same cycle, but if they are spread out in time, the currents are low, the peak current is less, but if they happen at the same time, the peak current is double, right? So that is the complication because the actual time of switching and the number of gates switching, all of that have to be considered, and the time of switching depends on the actual design and layout and so on. So it's a complex problem, even though the idea is simple, but it's still kind of people do it, but what I've heard from people from industry is that it's a painful thing to really get it right. I mean, there are no good tools to. Huh? So the question is, want all the logic switch at the clock, but if you see the first, you can think of it as layers. As soon as the clock edge happens, the flops switch, then the first layer of gates take it, and so on. So it's like you can think of it as a wave propagating down. The switching is like a wave which propagates down from the beginning flop to the capture flop. The other thing you have to watch out is these outputs. See, when you shut off this power gate, what happens to this VDD V? Why V? Because virtual. It's called a virtual VDD. You can also have this power switches in the ground. Then that becomes virtual ground. VDD V, what happens to this VDD V voltage? Where will that voltage be? Let us say this is a 1 volt. VDD is 1 volt. And when it's running, it's not in sleep, this VDD is say close to 1 because you did a great job of designing the power switch. When you shut off this, VDD will you cannot define, but it has physically what will happen, right? It will be some voltage, no? You can say I don't know. Correct. So what will happen is, see, there is some capacitor, and initially all these you'll have leakage current going, right? It will start discharging this. See, there will always be some capacitor. So VDD voltage will start falling. Eventually it can go all the way down to ground. When you turn it on, this has to charge up again, right? So you have to wait till it charges up before you can start using it because the voltage is not yet reached. So that is another thing. Going in, coming out, right? How long does it take? That is another thing to be considered. Also, when you turn it on, right, say this voltage is close to ground, you are essentially turning it on, and you'll have like a lot of current initially going into this node to charge up, right? It's like you have one capacitor shorted to ground, at ground, you turn on this power gate switch and there's a lot of current which will just rush in at that particular instant. When the current starts rushing in out here, you will have a voltage drop in this VDD outside here on this wires out here, which can affect performance of some other logic blocks. You turn this on, it creates noise somewhere else. So you see all these complications come in even to implement such a very simple idea. All these physical aspects have to be considered for you to be able to get this to work properly, engineer it properly. And then of course when you shut it on and all these volts signals go down, they are transiting down, slowly VDD is degrading. If this voltage, if this signal is fed to another block which is not power gated, which is still running at 1.2 volts or wherever it is, it's not good, right? Because the signals are decaying down. There will be somewhere in the intermediate voltage for a long period of time. So you have to protect it. And then of course, if information is there inside here in memories and so on, you lose all of that. So if that is important to you, you need to save it before you do something. And you can do something similar where you have certain flops mirroring the flop, and those flops are not power gated. They are connected to an external supply, VDD. Only VDD is connected to the flop in the core, but the slave flops, which are supposed to store during standby the state, they are connected to VDD, so they don't lose information. Okay, so with that I come to the last slide of this lecture. Before I close, any other questions?